Here are our Chapter 7 video enhanced lecture notes. In this chapter, which is entitled Atomic Structure and Periodicity, we have for our outline electromagnetic radiation, that is light, the photoelectric effect, atomic spectrum of hydrogen, the Bohr model, quantum mechanical model, and trends in atomic properties. This is a very long chapter with lots and lots of information. Whenever you need to look at an example or just redo a calculation as we had done, just stop the video and take your time to do that and come back when you're ready. So, light is something that we need to study in our class a bit. We'll have a little introduction to it, simply because so many techniques that we use in chemistry to study chemicals involves actually using light. You may have heard of UV visible spectroscopy, you may have heard of infrared spectroscopy. Those are using light. So we will study light a little bit. So light is electromagnetic radiation. It's composed of an electric field and it's composed of a magnetic field. In our diagram, the electric field is shown as the red oscillating up and down wave. Electromagnetic radiation, that is light, it travels, it moves from what it's reflected off to the next thing. And so it's an oscillating electric field moving up and down, actually simultaneously with an oscillating magnetic field moving up and down, actually left and right, perpendicular to the electric field, and it travels. So that picture there is trying to show this. Notice that the red, the electric field wave, moves up, moves down, up, down, and we describe light very commonly by looking at its wavelength. That would be the length of one wave. So it's actually a length as measured in distance, could be meters, could be nanometers, and it is the length of one wave. So going up, cresting, going through the zero line, going down, we call that troughing, going back to the zero line. That is the wavelength of this particular light. The electromagnetic spectrum, so the light spectrum, varies in wavelength. In meters, it's shown here in this graph or this diagram, from 10 to the minus 12 meters all the way to 10 to the fourth. There's many different types of light. The highest energy N is the gamma rays. They accompany nuclear reactions, very high energy, very short wavelength, very high frequency, very destructive. Next, a little bit lower in energy, we have X-rays. You've probably had an X-ray done of your teeth at some point. Next, we have ultraviolet radiation. We are exposed to that to some extent from the sun. That's why we're to wear sunblock, hats, glasses, and so on. Next in energy, so a little bit lower in energy, we have visible light. That comes to us from the sun, also light sources here on Earth. And the visible spectrum is actually a very narrow spectrum, a very narrow portion of the whole electromagnetic radiation spectrum. And it runs from violet, the highest energy end, which has a wavelength of around 4 times 10 to the minus 7 meters, or 400 nanometers, all the way to the red end, which has the wavelength of 7 times 10 to the minus 7 meters, or 700 nanometers. The highest energy end is violet, and then we have blue, and then we have green and orange, or yellow, then orange, then red. So the high energy corresponds to short wavelength and high frequency. The low energy end corresponds to longer wavelength, so we say long wavelength and low frequency. After visible, we have infrared radiation. Then we have microwaves. Those are what you probably have used sometime today to heat some food item in your microwave oven. After that, we have radio waves, which we use a lot when we listen to the radio. Going to our next page. So we have a wave. Light is a wave, much like a water wave. We describe the light wave by wavelength, by frequency, or by energy. So wavelength is the length of one cycle, so going from the zero line to the crest, back to the zero line, to the trough, and then back to the zero line. That whole wave, that length of that wave would be its wavelength. The frequency is the number of cycles per second. The energy of light is equal to h nu, where nu is the frequency, or in terms of wavelength, it is hc over the wavelength. The wavelength we call lambda. That's the Greek symbol lambda. So most commonly we're calculating the energy from the wavelength. So we're using the equation E equals hc over lambda, where lambda is the wavelength of the kind of light that we are working with. H and C are both constants. H is 6.626 times 10 to the minus 34 joule seconds. It's called Planck's constant. C is the speed of light, and its value is 2.9979 times 10 to the 8th meters per second. At least that's its value to that many sig figs. Looking at violet light, it is the highest energy end of the visible spectrum, and its wavelength is around 400 nanometers. And its energy, so of a 400 nanometer light, in the violet spectrum, if we wanted to know its corresponding energy, we would use the equation E equals hc over lambda. So we put the value for H in, put the value for C in, and then we divide by the wavelength in units of meters. So we have to convert from the 400 nanometers to meters, and you see the conversion there. 1 nanometer is 1 times 10 to the minus 9 meters. Units work out, the seconds cancel out, the meters cancel out, so we have just joules. So the wavelength, or rather the energy of that 400 nanometer wavelength light is 4.97 times 10 to the minus 19 joules. If we look at the other end of the visible spectrum, the red light end, where we have 700 nanometer wavelengths, and we're after calculating the energy of that one with that wavelength, we would do it just as we did with the 400 nanometer light, but we would be putting in 700 nanometers. We would calculate the energy to be 2.84 times 10 to the minus 19 joules. So make sure that you would get that same number. Do it yourself. What we have found is the energy of the red light is less than the energy of the violet light. Its wavelength is longer, 700 versus 400, and that means lower energy. So long wavelength means low energy. It also means low frequency. Gamma rays have the highest energy, the highest frequency, and the shortest wavelengths. And radio waves have the lowest energy, the lowest frequency, and the longest wavelengths. So the visible spectrum runs from violet down to red, violet the high energy end, red the low energy end. If you reverse that, you get Roy G. Biv, a little way for us to remember the order of the visible spectrum. So which flame is hotter, blue or yellow? Well, since blue is on our spectrum higher energy than yellow, we would conclude that a blue flame is actually hotter than a yellow flame. Okay, now we'll talk about interference. So imagine we have a child's pool of water, and it is very still. We're standing over it. We're holding two rocks, one in each hand. We have our hands separated by perhaps a foot, and we drop our rocks at the same time. So each one sets up a ripple that would look something like that diagram there. And as the wave emanates from where we dropped it, it peaks, it troughs, it peaks, it troughs. And where two peaks or two crests interact, one from the one pebble, one from the other pebble, where they interact, they make for what we call constructive interference, a big crest. Where two troughs meet, they make for a big trough, again, constructive interference. Where a crest and a trough meet, they make for what we call destructive interference. They make for no wave. So in our diagram here, the one on the bottom of the page, on the left side, when two crests add, we get a big crest. When two troughs add, we get a big trough. Those are both constructive interference. Where a crest and a trough meet, we get destructive interference. We get no wave. And realize again that these waves, the crests, the troughs, the crest and the trough, they are from one rock, one wave, the other rock, the other wave. So we have constructive and destructive interference occurring when waves meet. Now we talk about diffraction. So imagine you are at the ocean and you're watching the waves coming towards you. Now imagine there's some kind of a barrier out there. Maybe it wants to make for less destructiveness from the waves on the land. If the barrier is much wider than the waves, then it does cut off waves that hit it, and the waves that can pass through it do so unchanged. Now make that barrier much, much smaller, so there's only a small gap for the waves to come through. Well, if the gap tends to be only about as wide as the wavelength of the waves, it turns out the waves will get through it and they will bend around it. That's called diffraction. It's the bending of a wave around an obstacle. Diffraction only occurs for waves. That phenomenon of diffraction only occurs for waves. So now look at the image that's called diffraction and interference patterns. So now imagine we have in that diagram where we see S and a slit and then the lower S and a slit. So what we have is a wave that is coming through two slits, and the slits cause diffraction at each one. So now we end up with two waves that are both bent. They both underwent diffraction, and they're like coming toward each other, where their crests or troughs meet, we get constructive interference. Where their crest and troughs meet, we get destructive interference. Now make the wave not a water wave, but make it a light wave. Well, where the crests meet, we get a bright image. Where the troughs meet, we get a bright image. Where a crest and a trough meet, we get no image. So we get dark. On our screen there in the image, we see bright, dark, bright, dark. We see an image like that. Hold your fingers very close together and look at a light source. If you've got them close enough together, you will see this kind of fringe pattern. You'll see light, dark, and that's this interference pattern that you're generating using light, making for a slit that's very small between your fingers. In the early 1800s, Young, a scientist by that name, did this double slit experiment. That's the one in the second image there on the top of the page, and got a diffraction pattern. From that, he concluded that light is a wave. Electromagnetic radiation is a wave, because only waves undergo this diffraction and interference. Okay, so from that, it was established that light is a wave. The photoelectric effect shows that light actually is composed of particles. So electrons can be emitted from the surface of a metal when the wavelength of light shining on the surface is shorter. That is, the energy of the light is higher than a certain threshold. So looking at our diagram on the upper diagram on the left, we have a metal surface and we have light shown by the red wave hitting it. Well, if the wavelength is too long, or we could say if the energy is too low, or the frequency is too low, then there just isn't enough energy in the light to cause electrons to be emitted from the metal. Looking at the diagram below, where we have blue waves hitting it, that is to imply higher frequency, higher energy, shorter wavelength. The energy is great enough that the light hitting it is transferring some of its energy to the atoms on the surface, causing them to eject an electron. So light is a source of energy. You feel the warmth of the sun when you're in it. And the electrons are ejected due to that energy coming from the light source. So what we have is at higher energy, that is shorter wavelength, electrons are emitted. And the light then is thought of as energy, as a packet of energy, a particle that are called photons. So what we have from this is that light can be thought of as like a little packet of energy. And the shorter the wavelength, the higher the energy, the higher is the energy of the photons composing that light. So going to the third column of that table, what we have then is light has both particle and wave properties. This is called the dual nature of light. Diffraction shows wave properties, the wave nature of light. The photoelectric effect shows the particle properties, the particle nature of light. So we see two diagrams, light as a wave and then light as particles. Either way, the energy of the light can be described by E equals h nu, or as we will use more commonly, E equals hc over lambda, where again h and c are constants and lambda is the wavelength of the particular light that we are working with. Okay, so that's our introduction to light. So what we need to remember from that is The energy of light, the energy of a photon, is equal to hc over lambda. Okay, so then light was used by scientists to start to study matter. A scientist named Balmer studied hydrogen. So he had pure hydrogen in a tube, and he shone light at it, and he looked at what happened with it. He studied light, hydrogen in the late 1800s. Going to the diagram that doesn't have the rainbow effect look, the one just below it, we see what we call a line spectrum. It contains only discrete wavelengths. So in that diagram where we see high voltage, what we have is a container of pure hydrogen. It's kind of like a fluorescent light bulb, and we plug it in. So we supply high voltage to the light bulb of hydrogen. And we then take that light that is given off. You know how when you plug a fluorescent light bulb in and flip the switch, you get light? Well, if we do that with hydrogen, pure hydrogen in the tube, and then we use a prism to see the various colors of the light that the hydrogen is giving off, we see that the hydrogen spectrum produces 4 lines. That's the line spectrum. Okay, now let's take a regular light bulb, a fluorescent light bulb, plug it in, flip the switch. We get what's called white light out. So go now to the upper diagram. It turns out that that white light, if we use a prism, I'm sure that you've all seen this done before. If you have a prism hanging like in a window, you see the rainbow effect. You see the Roy G. Biv spectrum somewhere on your wall. And that is a continuous spectrum. We see all the colors of the rainbow, and they blend one into the next. Well, if we now replace that white light tube with our hydrogen tube, we see that we have not all the colors of the rainbow, but only some of them. We see 4 of them. We see a red line. Look at that arrow pointing down. You see in the diagram there, it looks kind of more orange than red, but in reality, it's more of a red color. It turns out the wavelength of that line is 656 nanometers. Then we see a green line, and that has a wavelength of 486 nanometers. Then we see a blue line with a wavelength of 434 nanometers, and then a violet line with a wavelength of 410 nanometers. So those are the 4 lines that we would get if we looked at hydrogen. They are the 4 lines that Balmer got when he looked at hydrogen. He took those wavelengths, and he basically just randomly and probably with a lot of persistence tried different functions to try to find some kind of function without any theoretical basis that would possibly somehow describe them. Here's what he and a scientist named Rydberg came up with, the Rydberg-Balmer equation. It's an empirical equation. An empirical equation is based not on theoretical work, but just on experimental work, like our PV is equal to nRT equation. What they came up with is the equation 1 over the wavelength, so like 1 over 656, equals R, where R is not the universal gas constant. It is the Rydberg constant, and its value is 1.097 times 10 to the 7th meters to the minus 1, inverse meters. Okay, so 1 over lambda equals R times the quantity 1 over n lower squared minus 1 over n higher squared, where n higher and n lower, the only restrictions on those are that they are integers, positive integers, 1, 2, 3, and so on, and n sub L is lower than n sub H. Okay, so let's do this example problem. Calculate the wavelength of light in the hydrogen emission spectrum, emission just meaning light is being emitted, given off, associated with the n equals 3 and the n equals 2 levels. I guess we could say n are like levels. Okay, so we use our Rydberg-Balmer equation. 1 over lambda equals r times 1 over n lower squared minus 1 over n higher squared. We have 1 over lambda equals, we put the value of r in, and its unit, times 1 over 2 squared, because that's n equals 2 is the lower one, minus 1 over 3 squared, and we get then 1 over lambda to be 1523611 meters to the minus 1, which when we inverse to solve just for lambda is 6.53 times 10 to the minus 7 meters, or if we convert that into nanometers, we get 656.3 nanometers. It is that red line that we see in the spectrum. So verify that you would get this yourself by running through that problem. Alrighty, so now we get into the section called the Bohr model. Scientists wanted to understand the physical meaning of the Rydberg-Balmer equation. What were those quantities, n lower and n higher? Scientists knew that atoms are neutral. Atoms are composed of protons, neutrons, and electrons. Protons and neutrons are in the nucleus, and electrons are in the electron cloud. And there's our diagram of the nuclear atom with the protons and neutrons in the nucleus, the electron around the nucleus in the electron cloud. The electron is attracted to the proton because of the opposite charges. There's a force of attraction between the two. And we're looking at hydrogen right now. So we have one proton, we have one electron. So we can visualize this like, with a gravitational force. The moon is orbiting the Earth, and it's moving. It's kind of like trying to almost escape. It's always moving away, as shown in the diagram there by the arrow, v describing velocity or speed. But the Earth is constantly pulling it back due to the gravitational force of attraction between the Earth and the moon. The atom we can visualize in a similar fashion. The electron is attracted to the proton via what is called not the gravitational force, but the electromagnetic force. But unlike the neutral atom, the electron is charged. But unlike the neutral moon, the electron is charged. Physics would tell us that accelerating charges, so that electron there with its charge, they are or have to be constantly emitting electromagnetic radiation. That is to say, an accelerating charge is constantly emitting electromagnetic radiation. It's constantly emitting energy. And if the electron emits energy in the atom, then what would happen is it would, instead of being able to sort of like stay in its space around the nucleus, it would slowly spiral into the nucleus. But this is not happening. Atoms don't collapse. So going back to the Earth and the moon. So the Earth is neutral, the moon is neutral. They're attracted to each other by the gravitational force of attraction between their masses. The moon is moving, so it's, you might say, kind of trying to escape, but the Earth is always pulling it back. It is not The moon is not losing energy because it's not charged. If it were losing energy, somehow it would go right into the earth, and because of that force of attraction. The electron, on the other hand, is not going into the nucleus. The atom is not collapsing. We know that because we're composed of atoms, and our atoms are not collapsing. We're alive. But the electron being charged, physics arguments would tell us that since it's accelerating, since it's charged, it would be constantly losing energy in the form of electromagnetic radiation. But that isn't happening. So this scientist named Bohr, Niels Bohr, he proposed a model where if the electron is in certain orbits, certain places around the nucleus called stationary states, it is stable. This constraint and classical physics gave rise to the Bohr equation. And this is the Bohr equation here, where the energy of the electron in a particular orbit given by the symbol n, where n can be 1 and 2 and 3 and 4 and so on, is equal to negative 2.178 times 10 to the minus 18, 1 over n squared, where E sub n is the energy at the orbit level n in units of joules. So what we have is Bohr proposed that provided the electron is at a particular orbit, it is accelerating, yes, but it is not emitting electromagnetic radiation, and the electron there is just moving about the atom, kind of like the moon moves about the Earth. It can move to a different orbit, but that orbit has to be determined by the Bohr equation. So the electron being the closest to the nucleus is the lowest situation. We call that state, when the electron is there in the n equals 1 level, we call that the ground state. So that would be the lowest energy state. It can absorb some energy and move to the n equals 2 orbit, a little bit higher energy, or maybe 3 or 4. It can even be kicked away totally from the nucleus. It would be put, in that case, in the n equals infinity orbit. Okay, now, if we put n equals 1 into our Bohr equation, we get the energy of that electron in that orbit to be negative 2.178 times 10 to the minus 18 joules. If we put it in the n equals 2 level, then we take that negative 2.178 times 10 to the minus 18 and we divide it by 2 squared, and we get negative 5.445 times 10 to the minus 19. Make those calculations for each of those orbits I'm showing there, and notice that when n equals infinity and the electron is completely separated from the atom, we would have in our equation negative 2.178 times 10 to the minus 18 times 1 over infinity squared. Well, 1 over infinity is 0, so the energy in that case is 0. Notice that the energies all have negative signs in front except for this E sub n equals 0. If we convert from the joules to times 10 to the minus 20 joules to try to get more of a sense of those numbers, we have that last column of numbers. So the ground state, the lowest energy state, has the energy of negative 217.8 times 10 to the minus 20 joules. And then we have the E sub 2 equaling to negative 54.54 times 10 to the minus 20 joules, and so on. So what we notice when we look at those numbers is the most negative number, the smallest number, is the n equals 1 ground state, and the biggest number is when n equals infinity and E sub n there is 0. If we put those on a number line, we would, showing the smallest numbers on the left side and then working toward the right, increasing, we could make a graph there of E sub 1, a little bit to the left of negative 200. There we see E sub 2, E sub 3, E sub 4. That is, E sub 1 is lower in energy than E sub 2, which is lower than E sub 3, and so on. So when we plug in our hydrogen tube, or we could say the same for when we plug in and turn on our fluorescent light bulb tube, what's happening is in the hydrogen tube, we have, of course, hydrogen with 1 proton, 1 electron. An atom absorbs the electrical energy. So we're supplying that voltage potential. So that's a source of energy. We call it electrical energy. So the atoms, many of them, within the tube, they're absorbing that electrical energy. This causes the electron to make a transition from n equals 1, the ground state, to some n higher level. Okay, so looking at our picture below, we see the an energy level diagram going from n equals 1 at the bottom of it, n equals 2, n equals 3, 4, 5, 6. So energy is increasing, going up. And if we have the electron in the ground state, n equals 1, and we give it some energy that I'm calling here energy in, energy absorbed, then it moves the electron from, in our diagram here, n equals 1 up to n equals 3. That's called a transition. So the electron is now up in this excited state, as we call it. But very quickly, the electron falls back down to a lower n level, a lower energy level. Now, the energy is conserved, so the energy of the atom goes down by emitting a photon of light, and the tube glows. If this, well, we see it glowing if the photon of light given off is in the visible spectrum. So notice in our second diagram there, energy emitted, that's I'm referring to in the diagram as energy out, by the atom in the form of light as the electron transitions from the n equals 3 to the n equals 1 levels. E out is light energy, a photon is generated. Okay, so when we have energy leaving the atom, the energy of the atom has gone down. When we have energy going into the atom, the energy of the atom has gone up. So that's what I mean by this E out and E in greater than, less than 0. So light is absorbed when the electron moves from low level to high level. Light is emitted when the electron transitions from a high energy level to a lower one. So when we plug that tube of hydrogen in, it starts to glow. Electrical energy is being absorbed, causing electrons to move from the ground state to a higher energy state. Very quickly, those electrons fall back down and they give off light in the process. If it's in the visible spectrum, we see that. So this process is called an electronic transition. The energy change of the atom is delta E, where delta E is E final minus E initial. The energy change of the atom is equal to the energy of the photon generated if energy is emitted. And so we have the energy change of the atom, the delta E, is equal to the energy of the photon, where we learned earlier that the energy of the photon is equal to hc over lambda. When the atom absorbs energy like electrical energy, the electron transitions to a higher energy level. When the electron in the atom transitions to a lower energy level, energy in the form of light is emitted. If the light is in the visible spectrum, we can see it. Okay, here's an example for us to do. Calculate the wavelength of light emitted when the electron in hydrogen makes the transition from n equals 3 to n equals 2. So there's our diagram showing n equals 3 down to n equals 2. Delta E is the final energy, E sub 2, minus the initial energy, E sub 3. So for E sub 2, we have from earlier the value negative 5.445 times 10 to the minus 19. For E sub 3, we have negative 2.420 times 10 to the minus 19. Those are both in joules. And we calculated delta E to be negative 3.025 times 10 to the minus 9. Energy is given off by the atom in the form of light. Okay, now we're after the wavelength. So we have the energy of the photon, E sub p, energy of the photon, is equal to this delta E. We want to get rid of the negative sign because we don't think of photons as having negative energy, so the absolute value sign there just implies if there is a negative sign, get rid of it. So we have hc over lambda for E sub p equals delta E. Solving for lambda, we get that lambda equals hc over delta E. We put in the value of h, 6.626 times 10 to the minus 34 joules seconds, and the value of c, 2.9979 times 10 to the 8th meters per second. And we divide by the delta E, negative 3.025 times 10 to the minus 19 joules, where we're dropping that negative sign. We calculate after looking at units. The seconds cancel out, the joules cancel out, we're left with meters. We calculate the wavelength to be 6.567 times 10 to the minus 7 meters, or 656.7 nanometers. That is the red line that we talked about earlier in the hydrogen spectrum. So now from this Bohr equation, we can understand more the physical meaning to the Balmer equation. His n lows and n highs were actually these orbits from the Bohr model. The energy change between any two energy levels in hydrogen can be calculated from delta E equals F equals E sub F minus E sub 1. So delta E is equal to E sub F, which is negative 2.178 times 10 to the minus 18, 1 over n sub F squared, that's the Bohr equation for the final, n sub final, minus a negative 2.178 times 10 to the minus 18, 1 over n initial squared. So for E final, we put the Bohr equation where we use n sub F, and for E initial, again, the Bohr equation where we use n sub initial. Delta E comes out to be negative 2.178 times 10 to the minus 18 times 1 over n final squared minus 1 over n initial squared. And the units here are joules. So if we're after E sub n, we would use E sub n equals negative 2.178 times 10 to the minus 18 times 1 over n squared. If we are after delta E, we would use this equation that we just developed here. Alrighty, now the energy change in the atom corresponds to a photon of light given off or absorbed. So we have that hc over lambda is equal to the absolute value of delta E, or lambda is equal to hc over delta E. And you could see what lambda would come out to be, hc over, putting in our delta E equation that we developed up above. And the units of the wavelength are meters, and drop any negative sign as the absolute value symbolism implies. So if we then do lots of calculations where we're looking at different transitions, n initial to n final, we have 3 to 2, 4 to 2, 5 to 2, 6 to 2, 2 to 1. Looking at the energy change for those different transitions, we would calculate them using the delta E equation in joules. So verify that you get those values yourself for those various transitions. We would calculate the wavelength of each one from its delta E, getting those numbers. And then if we convert from meters to nanometers, we have those numbers in the last column. So again, verify that you could calculate all those yourself. Remember from our study of light, we learned that the visible spectrum varies from about 400 to about 700 nanometers. So the upper four lines, the 3 to 2, 4 to 2, 5 to 2, 6 to 2 transitions, those are all in the visible spectrum. In fact, those are the only 4 in the hydrogen spectrum that are in the visible spectrum. The last transition from 2 to 1 is in the UV range. We would not see that with our naked eye. Okay, our next problem that I'll have you stop the video and do now or come back to later and do is calculate the energy needed to ionize ground state hydrogen. What that means is to excite the electron from n equals 1 up to n equals infinity. So use the delta E equation to make that calculation. Electronic transitions in the Bohr model for the hydrogen atom. So here's a diagram where the one down below on the left side is showing an energy level diagram. We saw those above. It is showing in the one with the concentric circles an orbit transition diagram. It's showing the transitions from, for example, 2 to, it must be 3 to 2, 4 to 2, 5 to 2. And then the lowest one, C, is showing the line spectrum. So you see the association between the transitions occurring in the atom and the line spectrum that we get out of analyzing those transitions. We get what is referred to as a discrete line spectrum, since only certain energies are allowed. Remember that in the Bohr model, the electron can only be in certain orbits. It can't be halfway between two orbits. It can only be at the one orbit or the next orbit or the one after or after. There's an infinite number of orbits, but they're all discrete ones. You can't, an electron just can't be anywhere about the atom. It's kind of like, imagine a staircase. As we walk up the stairs, we know that we can't put our foot halfway between two stairs. There's nothing there to support us. We could say kind of like stairs are quantized. Atoms are quantized. The electron can only be in certain places. The diagram on the most right side there, series of transitions in the hydrogen atom, what that is showing are many different transitions that occur, and they have names: Lyman series, Balmer series. The Balmer series is the one that we have been talking about. Most of those are in the visible spectrum. The next series, so of all those lines, the only ones that turn out to be in the visible spectrum are 4 of the Balmer series lines, the 6 to 2, 5 to 2, 4 to 2, and 3 to 2 transitions. Okay, so that's the Bohr model. Next we get into the quantum mechanical model. Well, unfortunately, it turns out the Bohr model is fundamentally incorrect. Scientists around the late 1800s, early 1900s, like Heisenberg, de Broglie, Schrödinger, they developed the correct model, what we call the quantum mechanical model. So as we learned, light has wave and particle properties. De Broglie proposed that matter has wave and particle properties. The energy equation of a wave, of the light wave, is given by E equals hc over lambda. The energy equation of matter is the famous Einstein equation, E equals mc squared, where m is the mass and c is the speed of light. If we equate these two equations, so hc over lambda equals mc squared, and we solve for the wavelength and we replace c by v for velocity, since we're not necessarily talking about light, we have v equals the speed of matter. What we end up with is an equation which would, if matter has wave properties, this is how we might calculate it. So we would take, we would use that lambda equals h over mv equation, put in our value for h, the Planck's constant, divide by the mass of whatever matter it is we're talking about, divided by its velocity. Alrighty, so let's make this calculation here, where we will calculate the wavelength of an electron with a speed of 3 times 10 to the 6th meters per second and a mass of 9 times 10 to the minus 31 kilograms. So we're using this equation, lambda equals hc divided, lambda equals h over mv. So we put in the value of h, 6.626 times 10 to the minus 34 joule seconds. We put in the mass of our electron, which is 9 times 10 to the minus 31 kilograms. And we put in the speed, 3 times 10 to the 6th meters per second. We would, from those numbers, get the value 2 times 10 to the minus 10 meters. If we convert to nanometers, we get 0.2 nanometers. So if this electron has wave properties, its wavelength would be 0.2 nanometers. And the way units work out, so go over to what I've got there on the right. So joules, seconds, over kilograms, over meters per second. Well, if we replace joules with its more basic units, kilograms, meters squared per second squared, and then we have times seconds divided by the kilograms meters per second, we see that kilograms cancels out, we see seconds cancel out, and one of the meters cancels out, leaving us with just the unit of meter length. So from this, we have this theoretical idea that electrons have a wavelength. Well, what we would have to do is verify that with an experiment. And electron diffraction was observed in 1926. So remember that waves, for something to undergo diffraction, it has to be a wave. It has to have wave properties. Maybe it has other properties too, but it has to have wave properties. So if we could get an electron diffraction pattern, then that would be the experimental backup to this idea that electrons are wave-like. And yes, a diffraction pattern was observed in 1926. Okay, our next problem for you to do on your own is to calculate the wavelength of a tennis ball with a speed of 20 meters per second and a mass of 0.1 kilograms. What you will find when you make that calculation is the wavelength is so very, very tiny, given the fact that a tennis ball is an object we can see. It's a macroscopic object. And its wavelength is so small as to be completely negligible and insignificant. And that's because of its large size and its slow speed. Whereas an electron is in the microscopic world, we cannot see it. It is, with our naked eye, it is so very tiny and moving so fast that its wavelength is not insignificant. Alrighty, so next we have quantum mechanics focuses on wave properties of the electron. So those wave properties that we just worked with, those are what the scientists realize that must be the important stuff to focus on. And that's quantum mechanics has been successful. Experiment backs it up, and it focuses on the wave properties of the electron. An electron bound to the nucleus is similar to a standing wave. They are not traveling, they are stationary. That's where that term standing wave comes from. So imagine we have a guitar, and standing waves caused by the vibration of a guitar string fastened at both ends. Okay, so that's our description of this diagram here. So take that guitar and pluck it right in the very center. So you have it bound at both ends. Those are called the nodes, and given in our diagram by the black dots. If you hit the string right in the middle, you get that 1/2 wavelength situation to occur. That's half of a wavelength, so the length of that string is equal to 1/2 lambda. If, on the other hand, we pluck it at the quarter point, we get the second picture down, the 2/2 wavelengths, as it goes back and forth, back and forth. That is, the length of the string is equal to 1 wavelength, or we could say 2/2 wavelengths. If we pluck it closer to a node, like at this third or a sixth of the length, what we end up with is 3/2 wavelengths, or the length is equal to 3/2 lambda. Notice in general that the length is equal to n/2 lambda. If we're saying n goes from 1 to 2 to 3 and so on, it's an integer. Now imagine the electron as a standing wave in the hydrogen atom. Only certain orbits have the circumference into which whole number of wavelengths will fit. That is, if we pluck that guitar string at a place where it can't set up a standing wave, a wave that can travel back and forth, that is multiples of 1/2 wavelengths, it's going to die out very quickly. Well, the same idea is true with the electron being a wave moving about the nucleus. It has to be able to be a standing wave. So it has to be at an orbit such that there's an integral number of wavelengths for it to make then a complete orbit around the nucleus. So hydrogen electron visualized as standing waves around the nucleus. The circumference of a particular circular orbit is equal to a whole number of wavelengths. That we see in A and B there. When n equals 4, we have that there are 4 wavelengths represented. Go ahead and count them. Go around it. The circumference. So the circumference is 4 lambda, or we could say n lambda. It's a whole number times lambda. In our n equals 5, go ahead and count it. It turns out there's 5 wavelengths expressed in that orbit that's a little bigger than the n equals 4 orbit. So circumference equals 5 times lambda, n lambda again. In this last one, there's a mismatch. N would be 4 1/3. That is to say, it's not a standing wave. It can't sustain itself. The electron could not be there. So the circumference is not equal to a whole number times the wavelength. In general, we have circumference equals n lambda. All other orbits produce destructive interference. Schrödinger worked out a model for the hydrogen atom in which the electron was a standing wave and restricted to certain orbits. This led to quantization, and this quantization fits observations. Alrighty, so there is the Schrödinger equation. H psi equals E psi, where you will study that more in upper division classes if you go into chemistry, if you go into physics. It's a very complex equation. It's basically an energy balance equation. Psi is called the wave function, and for us it's the atomic orbital. We're going to work a lot with atomic orbitals. It's an energy balance, and that's what the E there is. It's the total energy, potential energy, kinetic energy. We're not going to certainly solve Schrödinger's equation. Rather, we will talk about the results of it, the implications of it. We'll learn how to work with those. So when the equation is analyzed, many solutions for psi, many wave function solutions are found. These solutions describe atomic orbitals, which are locations where electrons can be found. So AO, atomic orbital. So in the Bohr model, we had the electron can be found in orbits. Well, it turns out the Bohr model was a little too simple, but it was a nice starting point. The electrons are found in regions of space called atomic orbitals, and we only actually know with 90% certainty that the electron is in any particular atomic orbital, as it turns out. So as we get into the results of the solving the Schrödinger's equation, whoops, I'm sorry, I'm not so good with this mouse. What we need to do is talk about several aspects. One of them is the Heisenberg uncertainty principle. So Heisenberg discovered that there is a fundamental limitation to just how precisely we can know both the position given by x and momentum given by the mass times the velocity of a particle at a given time. So what that means is, in the microscopic world, things are so tiny that we can't exactly know where they are and how they're traveling at the same time. There's a limitation to how much we can know about those quantities. And we have Heisenberg's uncertainty principle, and it is delta x, that is the uncertainty in the location, the position, times delta mv, the uncertainty in the momentum, the mass times the velocity. They are greater than or equal to h over 4 pi. The uncertainty in location and momentum are unimportant for macroscopic objects, because we can say for sure where a ball is, how fast it's moving, but are very important for microscopic objects. In quantum mechanics, we don't speak of the precise position of the electron, rather of the probability that the electron is at a given location. And the probability turns out to be psi squared. So looking at graph B, we have this being for the hydrogen atom. So far we're just studying hydrogen. We have so we look at probability versus distance from the nucleus. So the nucleus is right there at the distance 0. And then the probability of finding the electron peaks a little distance from the nucleus. That means that region is where it's most likely to find the electron. And that would describe the atomic orbital. So we have here in hydrogen, that peak position, that location of the atomic orbital, that atomic orbital turns out to be called the 1s atomic orbital in hydrogen. And that's where the electron is most likely to be found. But it can be found to the left or the right of that at smaller distances or greater distances. It's just not likely. Notice that the probability never goes to zero. The size of the 1s orbital is the radius of a sphere that encloses 90% of the probability distribution. 90% of the time, the electron is in this sphere. An atomic orbital is a region of space where there is a high probability of finding an electron. So it's like a little house with 90% certainty that the electron we're working with is in that. When we solve, when we solve Schrödinger's equation, we find that an atom has many atomic orbitals around its nucleus, and electrons can only exist in these atomic orbitals. Those occupied determine the energy of the atom, and when an electron makes a transition from a high energy atomic orbital to a low energy atomic orbital, energy is released as light. Quantum mechanics and spectral experimental work, they have shown that 4 quantum numbers are needed to describe the electron in an atom. So quantum mechanics, that's Schrödinger's equation, spectral work, so that's experimental work using light and so forth, they show that 4 quantum numbers are needed to describe each electron in an atom. And those quantum numbers are N, L, M sub L, and M sub S. N, L, and M sub L, they describe the atomic orbital. They're kind of like the address of the atomic orbital. M sub S describes the electron in the atomic orbital. So if the atomic orbital is like a little house, or maybe imagine a theater where your ticket tells you what section you're in, what row you're in, what seat you're in. Those would be like the N, the L, the M sub L. You yourself, sitting in the seat, you would be kind of like M sub S. So now looking at these quantum numbers, N is called the principal quantum number, and it can take on values 1, 2, 3, on up to infinity. It's not the N from the Bohr model, but it's definitely, we can kind of visualize it in a similar way. It's called the shell. So N is describing the shell. It's related to the size and the energy of the atomic orbital. So when N equals 1, that atomic orbital is in the region of space close to the nucleus. When N equals 2, it's a little further away. When N equals 3, a little further away. And remember that atoms, even small ones like, well, hydrogen, have many atomic orbitals about their nucleus. The electron can be in any of those orbitals depending on what energy it's absorbed and so forth. The N equals 1 would describe the lowest energy shell. It's the one putting the electron closest to the nucleus. L, that's not a 1, by the way, that's L. It's called the angular momentum quantum number. L takes on values 0, 1, 2, and so on up to N minus 1. So if n is 1, L can only be 0. If n is 2, L can be 0 and it can be 1. If n is 3, L can be 0, 1, or 2. L is referred to as the subshell, and it's related to the shape of the atomic orbital, also the energy. And for L, we can describe it with a number, like 0, 1, 2, 3, 4, and so on. We can also describe it with a letter. So the number and the letter are equivalent. It just depends how we are talking about it, which one we might use. When L is 0, the letter describing L is S. And S orbitals always have a spherical shape. When L is 1, those atomic orbitals are called p atomic orbitals. It turns out, as we will see, there are 3 of them. They have a dumbbell shape. They're composed of 2 lobes separated by a node. Remember from our guitar example, a node is where the string is attached, or where it doesn't go up and down at all. So when L is 2, then the letter describing L equals 2 is D. It turns out there's 5 of those possible atomic orbitals, and you see their shapes in the purple diagrams. When L is 3, the letter describing those atomic orbitals is F. Turns out there's 7 of those, and they have those bizarre shapes given by the green. So that's L, that quantum number. M sub L, what did I do? M sub L is the magnetic quantum number. M sub L has integral values varying from negative L to positive L. For example, when L is 0, M sub L can only be 0. When L is 1, M sub L can be negative 1, 0, or positive 1. When L is 2, M sub L is negative 2, or negative 1, or 0, or 1, or 2, and so on. It's related to the orientation of the atomic orbital in space relative to the other atomic orbitals. So we have the table 7.2. We also have the summary there. So when n is 1, we're talking about the shell closest to the nucleus. It turns out that L, which is 0, means there's only one subshell possible there. Because when n is 1, L can only be 0. So there's just one subshell. When n is 2, L can be 0 or 1. That is to say, there's 2 subshells. And those are the S and P subshells. When n is 3, L can be 0, 1, or 2. Those are the S, the P, the D orbitals. When n is 4, L can be 0, 1, 2, or 3. So we have the S, the P, the D, the F atomic orbitals. Look at the table 7.2. So we have like what we just went over in the table below. N equals 1, L equals 0. The designation for that atomic orbital is 1s. 1 for N and then S for L in terms of letter. M sub L can only be 0. There's only one orbital there. When N is 2, L can be 0 or L can be 1. When L is 0, we have a 2s atomic orbital. M sub L is only 0, so there's just one orbital there. When L is 1, we have the 2p atomic orbitals. M sub L can go from -1 to 0 to +1. That is to say, there are 3 atomic orbitals. So go down the line making sense of those. Now, whenever we have an S subshell, whenever we have L equals 0, or we could say L corresponding to S, because M sub L can only be 0, there's one atomic orbital. And that's what we were talking about in that table above. Each p subshell has 3 atomic orbitals. They are degenerate. They all have equal energies. Each d subshell has 5 atomic orbitals represented by these 5 lines. They are all degenerate, equal energy. And then each F subshell has 7 atomic orbitals. They are degenerate, have equal energies. How do we know that the 1, the 3, the 5, the 7, they are the M sub L that corresponds to that L value? And these are all just based on those restrictions in those quantum numbers. So as we were referring to above, the atomic orbitals are named according to the shell they are in. In the n equals 1 shell, we have just one 1s atomic orbital. In the n equals 2 shell, we have 1 2s atomic orbital and 3 2p atomic orbitals. In the n equals 3 shell, we have 1 3s atomic orbital, 3 3p atomic orbitals, and 5 3d atomic orbitals. When n is 4, we have 1 4s atomic orbital, 3 4p atomic orbitals, 5 4d atomic orbitals, 7 4f atomic orbitals. We can kind of think of these, we can try to make some kind of picture in our mind of like a theater. Have you ever been to a theater where the stage is round and the guests, the viewers, sit in rows around the theater? So picture that. The nucleus is the stage, and the chairs around the theater are the atomic orbitals. And on your ticket, if it's this kind of a theater where it's got the different sections, like the orchestra, the mezzanine, on your ticket it says what section you're in, having to do with, like in this case, the shell. If you're in the orchestra, that's kind of like n equals 1, you're close to the stage. If you're in the mezzanine, you're a little further away, maybe that's n equals 2, and the gallery, you're further away, n equals 3. And then within the section, you have a row that you're in. That could be kind of like L, like which row in that section are you in? We have to picture the rows as having different kinds of seats in them. Some that are like love seats, some that are regular sofas, some that are extra long sofas, and so on. So those are like M sub L. So the quantum numbers, the first 3, the N, the L, the M sub L, they describe the atomic orbital. They get us to our exact seat. which seat are we in the row we're in. So the seat would be M sub L, the row would be like L, and the section, the orchestra, the mezzanine, that would be like N. Now, once we get there, we are the person in the seat. That is our last quantum number that we have yet to talk about, M sub S. Okay, so putting this stuff together that we learned about for the atomic orbitals, we can construct an energy level diagram. So look at the atomic orbital energy level diagram for a multi-electron atom. So the lowest energy atomic orbital, the one closest to the nucleus, that's the 1s atomic orbital. All atoms have that as the lowest energy one. Next comes the 2s atomic orbital, a little bit higher in energy come the 2p atomic orbitals. They're drawn off to the side a little bit so that we space it out. Next in energy comes the 3s atomic orbital, next the 3p atomic orbitals, next the 3d atomic orbitals. Actually, between 3p and 3d, there's the 4s atomic orbital. It's just not shown on our diagram. Okay, and then we have on our diagram that 2p atomic orbital energy is a little higher than 2s, and that's what I'm showing here. When there are 2 or more electrons, the energy of the 2s atomic orbital is less than the energy of the 2p atomic orbitals. In general, E sub ns is less than E sub np, which is less than E sub nd, which is less than E sub nf. And that has to do with what we see in this diagram here. The 2s atomic orbital, if we looked at probability versus distance from the nucleus, we see that on the 2s diagram, the red line curve, we see that it has 2 peaks, one close to the nucleus, small, and one a little farther from the nucleus, but very, very high probability. We see the 2p orbital peaking at just one spot. It's a little closer to the nucleus than the big peak of the 2s one, but due to the small 2s peak being very close to the nucleus, what it means is if electrons can be in the 2s atomic orbital, they're at a lower energy than if they're in a 2p atomic orbital. All right, the fourth quantum number, that's m sub s. That's called the electron spin quantum number. And this one only takes on 2 values, m sub s equal plus 1/2 or m sub s equal minus 1/2. And they relate to how the electron is spinning about an axis through itself. We can picture it that way. If it's spinning such that the axis is pointing upwards, we call that m sub s plus 1/2. If spinning such that the axis is pointing downward, we call that m sub s equals minus 1/2. Take your right hand, put your thumb pointing upward, and bend your fingers. So that would describe the electron moving in kind of like counterclockwise fashion. Notice your thumb is upwards. To make your fingers bend in a clockwise fashion, your thumb is pointing downward. That would be the spin down. So the m sub s is describing the actual electron in that atomic orbital. Does it have a spin up or a spin down? The 4 quantum numbers, so n, l, m sub l, m sub s, they describe one electron in an atom. Like if we draw the electron with an arrow up if we're talking m sub s plus 1/2, or an arrow down if we're talking m sub s equals minus 1/2, because it's describing that how the electron is spinning. So let's say we have an electron in the 1s atomic orbital with the arrow up, the spin up. Its four quantum numbers would be n equals 1, L equals 0, m sub L equals 0, m sub S equal 1/2. Okay, now putting all this stuff together, we have an atomic orbital energy level diagram. And the orbitals are organized from lowest energy to higher energy atomic orbitals. And we saw a partial energy level diagram earlier, and here's another one where I've added some lines to separate the shells. So energy going upwards, lowest energy, we have the 1s atomic orbital. Next, we have the 2s atomic orbital. Oh, notice that the 1s atomic orbital, that's the only orbital in the n equals 1 shell. So the n equals 1 shell, done. And then we get to the 2s atomic orbital. Well, in the n equals 2 shell, we can have L equals 0, the 2s atomic orbital. We can have L equals 1, the 3 2p atomic orbitals. That shell is now done. Then we go to n equals 3. We have L equals 0, the 3s atomic orbital, L equals 1, the 3p atomic orbitals, and L equals 2, the 5 3d atomic orbitals. Now that shell is done. Well, it turns out energy-wise, the 4s atomic orbital is a little bit lower in energy than the 3d atomic orbitals. An electron in a 4s atomic orbital can get a little closer to the nucleus than if the electron were placed in a 3d atomic orbital. Alrighty, so in the n equals 4 shell, L can be 0, 4s, L can be 1, the 3 4p's, L can be 2, the 5 3d's, L can be 3. We would have 7 4f atomic orbitals. I'm just not showing them in this diagram, but they would be a little higher in energy than the 4d ones. We have something called the Aufbau principle, the build-up principle, and that states that we fill, when we have an atom and we're wondering where all of its electrons are within the atom, what atomic orbitals are they in, we fill from lowest energy and work upwards. We also have a principle called the Pauli exclusion principle, which states that no two electrons in an atom can have the same set of 4 quantum numbers. That actually translates to up to 2 electrons are allowed per atomic orbital, provided they have opposite spins. So in the 1s atomic orbital, we can have up to 2 electrons because the first electron would have quantum numbers 1, 0, 0, 1/2. The second one would have quantum numbers 1, 0, 0, negative 1/2 because it's got spin down. Notice they both have the first 3 quantum numbers 1, 0, 0 because that's the same atomic orbital, and that's what those first 3 quantum numbers describe as the atomic orbital. Those 2 electrons, we say, have paired spins. They are paired electrons. If we have only 1 electron in an atomic orbital, we call it an unpaired spin or an unpaired electron. Okay, so Pauli exclusion principle, we can have no electrons in an atomic orbital, 1 electron in an atomic orbital that we tend to draw spin up, or we can have up to 2 electrons, provided they have opposite spins. Hund's rule is the lowest energy configuration is the one having the maximum number of unpaired electrons in a set of degenerate atomic orbitals. Okay, so let's say we take p atomic orbitals. There's always 3 of them. They have equal energies. They are degenerate. If we have 2 electrons we're putting into those atomic orbitals, we actually spread them out. They would rather not be lumped together in the same atomic orbital because they do repel each other a little bit. So they wouldn't be that second situation. They wouldn't be paired. They would be unpaired in separate atomic orbitals. If we had 3 electrons, we would have 3 unpaired electrons. If we have 4 electrons, then we would have to start pairing. Okay, so we will fill the energy level diagram for various elements, and we will now talk about electron configuration. So the electron configuration, that is kind of like a shorthand way of showing the energy level diagram, and it is describing all of the electrons in an atom, whereas quantum numbers, the 4 quantum numbers, are the 4 quantum numbers of a particular electron in an atom. All right, so electron configuration, that's like a shorthand way to show where all the electrons are within an atom. It is done by showing for each orbital, it shows which orbital we're talking about, like maybe the 1s atomic orbital, and then as a superscript to the right, we give the number of electrons that are in that orbital or those orbitals. So we show the orbital as a superscript, we show the number of electrons in the orbital. Alrighty, so for hydrogen, we have 1 electron. Here's a partial energy level diagram. We put the electron in the lowest energy, and we say its electron configuration is 1s1. Hydrogen has 1 unpaired electron. For helium, we have 2 electrons. We put those both in the 1s atomic orbital. We make them have opposite spins, so they are paired. So its electron configuration is 1s2. For lithium, notice we are now in row 2 on the periodic table. By the way, get a periodic table and have that out for yourself, because there is a direct correlation between electron configuration and the periodic table. We don't have to fill in the energy level diagram to know what the electron configuration is for an element, as long as we know how to kind of read into the periodic table to see what it is. So get a periodic table out for yourself. Before we actually go to lithium, hydrogen and helium, those are the only 2 elements in the first row. Notice when we finish with helium, we have finished row 1. We've also filled up the n equals 1 shell. So there's a correspondence between shell and row. Lithium, we're in row 2, and we're in the n equals 2 shell. So we have 3 electrons, we put 2 in the 1s atomic orbital, of course paired, and we put the third one unpaired, pointing up in the 2s atomic orbital. So its electron configuration would be 1s2, 2s1, or we can note that 1s2, that's exactly the helium electron configuration, the noble gas coming before lithium. So for 1s2, we can put He in square brackets and then just finish off the electron configuration for that atom, for lithium. So we have helium 2s1. It saves a bit of writing when we get to bigger atoms to use this noble gas core notation. Beryllium. So we have 4 electrons, and we put 2 in the 1s, and then we put 2, make them paired in the 2s atomic orbital. The electron configuration of beryllium is helium 2s2, no unpaired electrons. Boron, 5 electrons, So we put the 5th in the 2p atomic orbital. Notice that when we went from lithium and beryllium over to boron, we had to make that big leap across. Boron, its electron goes into 2p atomic orbitals. Okay, so the electron configuration is helium, 2s2, 2p1, one unpaired electron. Carbon, we have one more electron. We put that in the next 2p atomic orbital, spin up. So electron configuration, helium, 2s2, 2p2. Carbon has two unpaired electrons. Going to nitrogen, we have one more electron, so now we have 3 unpaired electrons. Electron configuration, helium, 2s2, 2p3. Oh, yes, I didn't mention it, but even though in carbon, in nitrogen, those electrons are in different 2p atomic orbitals, we just write it as, for carbon, 2p2, for nitrogen, 2p3, but we have to know how they are oriented, that they are in separate 2p atomic orbitals. Oxygen, we have one more electron. Now we have to start pairing. So, let's see, wait a moment. Yeah. Okay, so oxygen, we have two unpaired electrons, and we could say, yeah, we have 3 pairs of electrons. Anyway, so its electron configuration is helium, 2s2, 2p4. Fluorine, yet one more electron. Putting that one in, we have the electron configuration helium, 2s2, 2p5, one unpaired electron. And then we get to neon, and we put that last electron in, the 2p atomic orbital, and its electron configuration is helium, 2s2, 2p6. Notice that neon completes row 2. Also, it completes the n equals 2 shell. Once again, that connection between shell and row. In our diagram there of this periodic table, we will see that the 1a, 2a elements, those all have their last electrons in the s atomic orbital that corresponds to their row. So, or period, we see row 1, 1s, row 2, 2s, row 3, 3s. And then we go to the yellow block of elements, and that would be boron in the top yellow row, row number 2. Boron, carbon, nitrogen, oxygen, fluorine, neon, all of those have their p electrons in 2p atomic orbitals, and all of the atoms in that yellow block have their last electrons in p atomic orbitals, and the p atomic orbital corresponds to the row that they are in. The 3a column always has 1 electron in the p atomic orbital. The 4a, 2. The 5a, 3. That would be nitrogen, for example. The 6a, 4. The 7a, 5. That would be like fluorine. And then the 8a, the p atomic orbitals are full. So, correspondence between the energy level diagram and the periodic table, and how we can then just read the periodic table to get the electron configuration. Okay, now I hope you've got that periodic table in front of you. Otherwise, pause and go get one. Nitrogen, or no, we're at sodium. So sodium has 11 electrons. If we put them in our energy level diagram, we would find that the electron configuration is, if we did helium, we would say 2s2, 2p6, 3s1. Or if we went to neon, which is the one that we just finished up above, let's see if I can get that back on the screen and still have this here. Well, anyway, here's neon, helium 2s2, 2p6, and then we have sodium, helium 2s2, 2p6, 3s1. Take the helium, the 2s2, the 2p6, that's neon, so we can replace all that stuff with Ne in square brackets and then finish it off 3s1. So run through and determine what the electron configuration would be for magnesium, aluminum, silicon, and so on. Coming to the end of that row to argon, we have that it would be the electron configuration of neon, and then 3s2, that would cover sodium and magnesium, and then 3p6, that would cover aluminum all the way then through the argon. So reading the periodic table and getting electron configuration from it is very powerful. So after argon, we have potassium. It's in, so the electron configuration for it would be the noble gas coming before it, argon, and then it is in row 4, and all of the elements in that 1A column have one electron in their s atomic orbital, their outermost s atomic orbital. So potassium, row 4, it would have the electron configuration argon 4s1. Calcium, all of the elements in the beryllium, magnesium, calcium, etc. column, the 2A column, they all have their outermost s electrons in the row they are in, S, and then 2 of them. So calcium, electron configuration argon, and then 4s2. Now we come to scandium. Scandium has one more electron, and so if we go back to the periodic, or to the energy level diagram that we have here on page 15. Okay, so we see that after the 4s atomic orbital energy, when we've got the 2 electrons there, as we did with calcium, we put our next electron at the next energy level atomic orbital, which is one of the 3D ones. So let's go back down here. So for scandium, then its electron configuration is going to be argon, the noble gas coming before it, and then 4s2, that gets us through calcium, and then it's a 3D atomic orbital it's in, and there's only one of them. So what we have to remember when we get into the elements that are these transition metal elements, the ones in our periodic table on page 16 in the purple block area, we have to remember that the row is one bigger than the D atomic orbital. That is, the scandium row starts, well, has 3D atomic orbitals. The yttrium row, that's 4D. The next one is 5D, the next one 6D. we just have to remember it's like off by 1. Otherwise, we just read the periodic table. Going to zinc, so that has 10 d electrons as we count over. And we have its electron configuration being argon, 4s2, and then 3d10. Notice that if you look at the total number of electrons zinc has, 30, and you put them in the energy level diagram, you would notice that you have filled the 3d atomic orbitals. Also, you're at the end of the purple, the block here. You're at, look to where zinc is on your periodic table, and you have completed the 3d atomic orbitals. Also notice there's a change in the periodic table as far as it goes from, in that diagram, purple to the yellow ones. All the purple section, we call them the D block. All the yellow section we call the P block. The blue section, the S block. Go down below to the green block, we call that the F block, because that's where we first start getting into the F elements. So gallium, that would be, have the electron configuration argon, 4s2, 3d10, and then 4p1. Notice that we're being in the P block, we're back to the correspondence between shell and row. Okay, so here's a periodic table with partial electron configuration shown. So make sure that you make sense of it. Let's look at element lead, atomic number 82, Pb. So it has 82 electrons. If we put them in the energy level diagram, we'd figure it out and so forth. But let's read the periodic table to get what its electron configuration is. Now, we have to follow the atomic numbers. We have to go from one to the next, to the next, to the next. Okay, so its electron configuration, we would write xenon, because that's the noble gas coming before it, xenon, and then we're over in row 6. So we have xenon, we're at cesium. We would write 6s2, that gets us through barium. Then we go into the purple block. Now, if we look at the numbers there, 57, it jumps to 72. What we have to do is go from 56, 57, we have to go down through into the green block, the lanthanides. So we have 56, 57, there we see 58. Now, something you have to remember is these are F atomic orbitals represented by the green block. The first F atomic orbital appears in the n equals 4 shell. So this first row in the green block is the 4F row. The row below it is the 5F row. Okay, so lead, going back to lead, we have xenon, 6s2, then we jump down, 4F, count across, 14, go back to the purple block, and then we have 5d10, that gets us through mercury, and now we're back to row and shell corresponding, so we have 6p2. So once again, xenon, 6s2, 4f14, 5d10, 6p2 for the electron configuration for lead. Valence electrons, those are the outermost s and p electrons. So if we look at gallium, its outermost shell is n equals 4. So we go to the electrons that are there in s and p atomic orbitals, and we see that there are 3 of those. Those are the outermost electrons. Those are the ones that feel the outside world. Those are the ones involved in bonding. Those are going to be what are important to us as we look at bonding. Valence electrons. The core electrons are all the inner ones. They're all the electrons represented by the argon electron configuration symbolism and all those 3D electrons. Those are the core electrons. Okay, here's a few problems for you to do. What is the electron configuration for antimony? How many unpaired electrons and valence electrons does it contain? What is the electron configuration for astatine, and how many unpaired electrons and valence electrons does it contain? Now, valence electrons. So we got an introduction to what they represent, the outermost s and p electrons. Well, all of the elements in group 1a, the hydrogen, lithium group, they have only one valence electron. All of those in group 2a, they have 2 of them. And then we jump across to the pink group, because remember, we're counting the outermost s and p electrons. So we're not counting d's and f's. So we jump to boron. All the elements in the boron column have 3 valence electrons. They have 2 s1s and 1 p1. The carbon, the 4a column, they all have 4. The nitrogen column all have 5. Oxygen all have 6. Fluorine all have 7. And lastly, the column of the noble gases, they all have 8 valence electrons, except for helium, which only has 2 because it only has 2 electrons. Notice the terminology there, the S block elements, the blue ones, the D block elements, the orange ones, the P block elements, the pink ones, and the F block elements, the green ones. Okay, these next couple of problems are, can the following quantum numbers describe an electron in an atom? Okay, so we have n equals 3, L equals 2. So that corresponds to d atomic orbitals. So we have 3 d atomic orbitals. We have m sub L equals -2. Yep, that's a possibility. And we have m sub S equal plus 1/2. So yes, we would say that these could describe an electron in the atom. It would be a 3D electron with spin up. Okay, so do the next couple of problems, just deciding if there's any violation in the rules of the quantum numbers. You know, remember the restrictions. N can only be positive 1, 2, 3, 4, and so on. L can go from 0 up to only n minus 1. M sub L is somewhere, but it's an integer, positive, negative integer between negative L and positive L. And then m sub S can only be plus 1/2 or minus 1/2. Okay, our next example is give the maximum number of electrons in an atom that can have these quantum numbers. Alrighty, so when n equals 2 and L equals 0, we're talking about a 2s atomic orbital. How many electrons can it hold? 2. So that's how you do those problems. So there's 2 more there for you to look at. Now we will talk about trends in atomic properties. We'll look at the atomic radius first. Here's a model, kind of a simple one, but basically the one that we will use. So looking at lithium, which has electron configuration 1s2, 2s1, it has 2 electrons that are in the first shell and 1 electron in the second shell. So we could make a picture, something like what I've shown here. Now, the size is determined by the outer electrons. The farther they are from the nucleus, the bigger the atom, the bigger the radius. The inner electrons shield the outer electrons from the full effect of the nucleus. Z effective, remember Z is the symbol for the atomic number, the number of protons. Z effective is the nuclear charge, so the number of protons, minus the shielding electrons contribution. And it's approximately equal to the number of shielding electrons. So there's the nuclear charge of 3, there's 2 shielding electrons, so Z effective is roughly 1, Z effective that outermost electron feels. In a better calculation, it turns out to be 1.28, so not too much different. This table here shows Z effective across the lithium row. Okay, but go to that next diagram, the next table. So there we have lithium with its Z effective of about 1. Now, looking at fluorine, which has the electron configuration 1s2, 2s2, 2p5. So it has 2 of the core electrons, and then it has 7 of the valence electrons, 7 in the next shell. Yes, some of them are s electrons, some are p, but if we, in this simple model, just put them all together as in that shell, that region of space, all 7 of them, we could have a picture kind of like what I've drawn there. So Z effective is 9, the number of protons, minus the inner 2, minus 2, or about 7. What that means is those outer 7 electrons, each one of them roughly feels a pull inward of about positive 7, as opposed to what the lithium outermost electron feels, pulling it inward, of 1. So each of those fluorine outermost electrons are being pulled in a little bit more tightly than lithium's outermost electron due to the larger Z effective in fluorine. Across a period to the right, Z effective increases. Across a period to the right, there's the same number of core electrons and the shielding electrons, but more protons. Thus, there is a greater nuclear attraction and the atomic radius decreases. So it decreases from lithium to neon. It decreases from sodium to argon. Now, looking down a group, so going down a column on the periodic table, if we again work with lithium, and this time we compare it to the one just below it, to sodium. Please have that periodic table out so you can refer to it as you go through these notes with me. So sodium has the electron configuration 1s2, 2s2, 3s1. So if we put those electrons in the simple model picture, we would have this. Now there are 10 core electrons, so Z effective is about 1 in sodium as it is about 1 in lithium. But in sodium, that outermost, that 3s electron is a whole shell away, a whole shell farther from the nucleus than the shell in the lithium atom. So that makes sodium bigger. So going down a column, Z effective changes very little. It increases a bit. Going down a column, N increases. Therefore, going down a column, the atomic radius increases. So we see the diagram that is shown there, how roughly the sizes are given. They're given in picometer, where 1 picometer is 10 to the minus 12 meters. So you see the numbers in case you need them in a calculation. You see a diagram showing the relative sizes. So our trend is to increase down and to increase toward the left, making the stuff in the bottom left corner big. So that's our atomic radius trend. Now, if we look at ionic radius, what we have to compare are the number of protons and the number of electrons. So in lithium, the atom, 3 protons, 3 electrons. We saw how they were distributed in a diagram above. In Li+, we still have 3 protons, but we have only 2 electrons. What that means is those 2 electrons aren't repelling each other quite as much as the 3 electrons in Li, the atom, are, making lithium plus, Li plus, a bit smaller than lithium, the atom. Cations, of course, are formed by losing electrons, and this reduces the electron-electron repulsion, so the size of the cation is usually smaller than the anion, or from the atom from which it is formed. The size of the cation is smaller than the atom from which it is formed. Okay, so now we're comparing fluorine, the atom, and fluorine, the F minus anion. They both have 9 protons. Number of electrons, F the atom has 9, being an atom, same number of protons and electrons. F minus has 1 more electron. Well, 1 more electron means a little bit more repulsion. It causes F minus to be a little bit larger than F the atom. So anions are formed by gaining electrons. Number of electrons increases. This increases the electron-electron repulsion, and often the size of the anion is larger than the atom from which it was formed. And in that next diagram, I show sizes of the atom versus the anion or cation that it forms. Isoelectric. So two isoelectric atoms, ions, they have the same number of electrons. So they have the same kind of shielding going on. O2 minus and Al3 plus, if you look at the electrons, they both have 10. Of course, oxygen has gained 2, aluminum has lost 3. If you look on the periodic table, they both have the electron configuration of neon. They would be isoelectric with neon as well. Now, in deciding which one of those two, O2 minus or Al3 plus, would be larger, since they have the same number of electrons, we look at the protons. The one with a larger number of protons is going to be the smaller one. It has a greater pull, a greater Z effective. So Al3 plus, more protons, so it's going to be smaller. And I have there in the table the of O2 minus, F minus, Na plus, Mg2 plus, Al3 plus, their relative sizes. Those are all isoelectronic with neon. So then we just start looking at numbers of protons. Here's a few atoms to compare and ions. And the next diagram is sizes of ion radii related to positions on the periodic table. Okay, so that's that trend. Our next trend we'll talk about is ionization energy. It's the energy required to remove the highest energy electron from an atom or an ion in the gas phase. So we could represent that by this reaction here, X gas yielding X plus gas plus an electron. That would be its first ionization energy. X being in its ground state if we're starting with an atom. So lithium gas forming Li plus an electron, that would take 520 kilojoules per mole. That's its first ionization energy value. If we take Li plus, so we've now already got an ion and we're removing one more electron, that E2, that process to remove that second one, is 7,300 kilojoules per mole. It's much larger since it's harder to remove an electron from an ion than it is from the atom. So also this second electron in the case of lithium is a core electron. Okay, example, in considering the first four ionization processes for aluminum and their accompanying energy, state-wide E4 is much greater than E3. So we have aluminum losing its first electron, 580 kilojoules per mole, Al plus forming Al2 plus, 1815 kilojoules per mole, so definitely going up. It's harder to remove an electron from something already positively charged. If we go from 2 plus to 3 plus, the energy for that, the I3 goes up because again we're taking yet another electron from an already charged substance, a positively charged substance, in fact a 2 plus charged substance. But when we go from Al3 plus to Al4 plus, we see a huge extra amount of energy required. That has to do with the fact that that fourth electron is being removed and is a core electron. So if we look at that table 7.5, we see sodium has, of course, only one electron that is not considered its core electron, so it's got one valence electron. Magnesium 2, notice the big gap between E2 and E3 for magnesium. Aluminum we talked about, and so forth. So it's easier to remove valence electrons than it is core electrons, so it takes less energy. It always takes energy to remove an electron. Notice all those were positive. So this is showing the trend. So they increase from left to right across a period and decrease down a group because the bigger is the atom. Let's say we're picturing removing an electron from an atom. The bigger is the atom, like lithium is bigger than neon. The bigger is the atom, the farther is the nucleus from the electron, the less hard, the less bound the electron is to the nucleus. When we have the nucleus close to the electron, like we do with neon in comparison to lithium, the attraction is greater because they're closer to each other, so it's held more tightly. So our trend is to increase like this. So the elements down at the bottom left of the periodic table have the low ionization energies, top right have high ones. And we see it shown as a graph by periods, and we also see numerical values shown on a periodic table. So use those values if you need to for calculations. Okay, so then we have that example problem to look at in each group of atoms which has the higher E sub 1. So base that on trends, that trend we talked about. Electron affinity, it is the energy change associated with the addition of an electron to a gaseous atom. So that reaction we could symbolize as X sub G plus electron yielding X minus G, so gas phase. So we're adding an electron. The electron affinity describes the energy required. Unlike ionization energies, electron affinities can be positive, endothermic, taking energy, or negative, exothermic, releasing energy. When the electron affinity process is exothermic, so we're looking at releasing energy, the more largely negative it is, the more energy is released. And notice if we compare fluorine and oxygen, fluorine has a much larger release of energy. If we look at phosphorus, sulfur, chlorine, because those are in the same period on the periodic table, we see that as the size gets smaller, the amount of energy released when an electron is added to the atom goes up. So the smaller it becomes, this is not a trend that always holds true by any means, but the smaller has the greater electron affinity in a very general sense for energy being released. Compare, for example, chlorine, bromine, and iodine in table 7.7. So chlorine is the smallest of those three, chlorine, bromine, and iodine. We're ignoring fluorine for a moment. And it has the greatest release of energy because the nucleus is the closest to where that electron can come, so it would be the most attracted to it. But there's many discrepancies in the electron affinity trend. So in general, more energy is released going left to right across the period. That's when energy is released, but it's only in general. And as we talked about, the nucleus is farther from the electron in the big one, moving toward the right to being a smaller atom, so the nucleus is closer to that added electron. Like I wrote, increasing that way toward the right with energy release, but with exceptions, many. Electronegativity. It is the ability of the atom to attract shared electrons to itself. This is a concept that we will very much use in chapter 8. I bring it up here because it's a trend in the periodic table, so I want you to think of it in that sense. So I brought it here into our chapter 7 notes. Electronegativity, En, it increases from left to right across a period and decreases going down. So that is all like these other ones related to size. Electronegativity, that's the ability of the atom via its nucleus to attract shared electrons. So imagine we have two atoms bonded together. The electrons that are bonding them are in the center between the two nuclei. So it's those electrons we're talking about. So the smaller is the atom, the closer it can get its nucleus to those shared electrons. So the electronegativity would be the greatest in our diagram there for the smaller atom. And they get smaller as we go from left to right, so the electronegativity increases, and that's why it increases from left to right. It decreases going down because they're getting bigger, so the nucleus is farther from those shared electrons. Calculated electronegativities were made by a scientist named Pauli, and the range is 4 for fluorine to 0.7 for cesium. So notice fluorine is the greatest, and then on the opposite corner on the periodic table we have cesium, which is small. Notice that the noble gases are not included there because rarely do they form bonds. They will. The bigger the noble gas atom, the more likely it is to do bonding, but they would really rather not, and they have what they need. They really don't want more electrons, so that's why they're not included here. Okay, so we have some examples here. Order these in these atoms in order of increasing atomic size, and then we have some atoms increasing ionization energy, the first one. Then we have the electron affinity, trend to think about. Then we have electronegativity. After that, we just have answers to problems. So we are done with these lecture notes. Now, make sure that you go back through your handout doing all the problems. If you haven't done them already, do them again if you have done them already. You may, of course, listen to this video or parts of it as often as you need to.